So today I'm going to be talking about astrostatistics in the era of large surveys from the Milky Way to individual stars. And so this talk is really going to be broken up into two parts, one about the Milky Way and then one about individual stars. And I'm going to start with the Milky Way. And it's Friday afternoon, and I know everyone here is an expert astronomer, so you already know about dark matter and everything. But, you know, it is Friday afternoon, so let's go through the basics and kind of refresh our memory. Okay, so dark matter we know is one of the biggest mysteries in astronomy, right? We know that of all of the matter in the universe, it should make up more than like 70% of the matter. So if this jelly bean jar represented all of the matter in the universe, then the black jelly beans would be all of the dark matter that we can. And one reason we're interested in dark matter is because we believe that every galaxy in the universe is sitting within its own dark matter halo. And we also see evidence for dark matter halos in clusters of galaxies, right? And when we look at galaxies in a much, when we look out into the universe and map all of the galaxies there, we see this hierarchical structure, right? And we can't recreate this structure in the universe unless we include dark matter in our simulation. And so there's all these lines of evidence that dark matter exists, but we actually don't really understand exactly what kind of subatomic particle is, or exactly what its distribution is, its spatial distribution is in individual galaxies. And so this is why I've been interested in estimating the mass of the Milky Way, because the mass of the Milky Way is dominated by its dark matter halo, and if we can better understand how much dark matter is there, how it's spatially distributed, then that could tell us something about the nature of dark matter and how it affects galaxy evolution in the universe. So I'm definitely not the first person to do this. People have been estimating the mass of the Milky Way for years and years. This figure, I guess, is about 5 years old now, but it's a collection of a bunch of different mass estimates of the Milky Way, all normalized to M200. And you can see that they really don't agree with each other, right? And not only that, but their error bars don't always overlap. So the mass of the Milky Way is incredibly uncertain. And there's a variety of reasons for this. One is that people use different methods and different data, and they make different assumptions. And it's also just a really, really difficult problem to tackle because we can't even see this dark matter. So the approach that a lot of people take, and I take as well, to use what's called kinematic tracers. So these are objects orbiting around the galaxy that we can see. They might be halo stars, they might be a stellar stream. In this case, I've highlighted globular clusters. Right? So if we look at the positions and velocities, then there are these mass estimators, which can take some sort of weighted average of the positions and velocities, might make some sort of assumption about the velocity dispersion of these systems, and then you can estimate the mass. Okay, but there's lots of challenges with using these kinematic tracers. And that's something that I focused on during my PhD and afterwards during my postdoc. So one of the challenges is related to the fact that we do not sit at the center of the galaxy, right? We're sitting out in the disk somewhere, maybe in between spiral arms or in one of these little spurs. That's still kind of uncertain. We're in the disk, right? So we have dust extinction and all sorts of things. And not only that, but because we're at this position, when we look out at, say, a globular cluster, and we measure its position and velocity, we're measuring it from our own reference frame, our heliocentric reference frame. And our mathematical models are much simpler in a galactocentric reference frame. So we have to transform these measurements from heliocentric to galactocentric. And we can do that if we have the full velocity components measured, and we can assume things about the solar motion, the rotation of the disk, and so on. We can do that transformation. But this is difficult when we have incomplete data. So for a long time, pre-April 2018, we didn't have proper motions for about half of the globular clusters in the galaxy. And so that makes things more uncertain. People would either use mass estimators that don't use any of the proper motions that we know and use only line of sight velocities, or they would throw away any data we have that's incomplete and only focus on the data that was complete. So in either case, you're throwing away some of the information that we had. Another challenge that's associated with this is that there are measurement uncertainties, right? And so these measurement uncertainties, they can be a function of distance, and propagating these measurement uncertainties from heliocentric to galactocentric can be a very nonlinear problem, and we might not understand exactly how that works. Another assumption is that we have to assume something about the population of these tracers. So we might assume that most of the tracers are following radial type orbits, or most tracers are following tangential type orbits, or maybe there's some isotropic mixture of the two. And the parameter that we usually use to quantify this is the velocity anisotropy parameter, right? It looks at the ratio between the tangential and radial velocity variances or dispersions. So what people have done in the past is they'll assume a value for beta and then get a mass estimate. But it's been shown that this can lead to biases in mass estimates. Okay, and another challenge that I always like to highlight is interpretation. Because there's obviously different methods that people use, not just the kinematic tracers, but people they also report the mass at different distances from the center of the galaxy. So on this plot, I have the mass within some radius from the center, and here's the radius along the horizontal, and you can see there's a whole bunch of different mass estimates here. And even at 50 kiloparsecs, there's a lot of different measurements with different error bars, and some of them overlap and some of them don't. And as you get further out in the galaxy, it gets more and more uncertain. And so how do you interpret these kind of results from these different studies, right? What are we supposed to make sense of the total mass of the galaxy when we're getting such a variety of results? So what I've been interested in doing is taking a Bayesian approach. So I always like to include Bayes' theorem here on the board, right? So this is the posterior distribution of the model parameters given your data. And I could go through the regular introduction about Bayes' theorem. I think a lot of people here probably use it. So I'm going to take this opportunity to tell you about a teaching method that I've developed to teach Bayesian analysis to students. And this uses M&Ms. So the basic idea is that you introduce Bayes' theorem to your students and you say, here's the posterior distribution. It's the probability of your model parameters given the data, right? So theta is your vector of model parameters, y is your data. And this is proportional to the likelihood times the prior distribution. And so the likelihood is where you can put in your model about how you think the data is distributed, and the prior distribution is where you can put in prior information you might have about the model parameters in that distribution. And so with the M&Ms activity, what you can do is ask the students to find the posterior distribution of the percentage of blue M&Ms that are made at the factory using Bayes' theorem. And this is fun because usually students have eaten M&Ms, so they have prior information. Okay, and it's also analytic. You can set this up analytically. So you can help the students along and say, okay, theta is the percentage of blue M&Ms produced in the factory. That's the parameter we're interested in estimating. And then imagine I gave you some data that are M&Ms from only one package, so you have a small sample size. And then you ask them, what's the likelihood? What's the prior information? So you can talk a little bit with them and point out, okay, well, when you draw an M&M from the bag, it's either blue or it's not blue, right? So what kind of likelihood might you want to set up for this? How about it? Yeah, Catherine's saying it. Binomial. Exactly. So it's a binomial distribution, okay? And so you can talk about the parameter of the binomial distribution here is theta. And then you can ask them about their intuition about the percentage of blues. And you can try to draw out, well, how many colors do you think are in the bag? And how often have you seen a blue come up in the past when you've eaten M&Ms before? So you talk with them about this and then get them to sketch out what they think the percentage of blue M&Ms is. It's kind of a probability distribution. And you say, okay, but what you drew, it doesn't have a mathematical form. How can we make it mathy, right? And so you can say, well, what's a conjugate distribution to the binomial, conjugate prior, and that's the beta distribution. So after they've done their sketch, then you say, this is the conjugate prior. It has hyperparameters, alpha and beta, right? And so I want you to find alpha and beta that match kind of your sketch that you've made. So this is the prior that my class chose when I was at UW and I developed this exercise. The class agreed that alpha equals 2 and beta equal 9 represented what they thought were the percentage of blue M&Ms. Okay, so you do all this, and I like to hide the fact that I'm actually going to give them M&Ms, because then at this point you give them the M&Ms and they're like, oh, they're really good. So you give them the M&Ms. I do have a story about Canadian M&Ms and US M&Ms though, so yeah, ask me that afterwards. Okay, okay, so here's our posterior distribution. You can also ask them, once you've simplified the likelihood times the prior, what's the kernel of this distribution now, right? And it takes them a minute, but they usually see this as also a beta distribution, because you can see there's still the chunk -1 and then this chunk -1. So it's still a beta distribution. It's analytic. They already have the code to plot a beta distribution. They just need to reparameterize it. So they open their data, and they get the results, and then they can plot the posterior distribution. So I did this too with my class, and I took out the first 10 M&Ms in my bag to get a really small sample size, and 4 of them were blue. And so this was the prior distribution, and then the dashed line is the posterior distribution. So it did actually change. But one thing, then what you can do is collect all the data from the class and show them how the posterior changes when you have more data. And so this is the class posterior distribution, and you can see it's much narrower, and it's centered around like 23% or so. And what's interesting here is if you were to naively just look at this and say, well, it's 25%, if I just did kind of a frequentist approach, but it's in what we actually estimated was more like 22 or 23%. And that's because the prior is having some influence, right? It's taking into account our prior information. Okay. So there's a surprise twist, and this is my favorite part of the exercise. There's actually 2 factories of M&Ms that make M&Ms, and they make different distributions of colors. So I don't know why, but New Jersey, they make about 25% blue M&Ms, and Tennessee makes about 20.7%. So what you can then do is ask them, predict which factory your M&Ms came from. And so some of them will look on the back of the package. It says New Jersey, but that's actually not where the code is, so it doesn't give them the right answer. The code is actually written near the barcode. You'll see either HKP or CLV. And so if you look at the package, you can see there's the HKP, and so our M&Ms actually did come from the New Jersey factory. So it's a fun little exercise. I've done it a few times with many different groups, and they always think it's fun, so I like to share it. Yeah. And also, after doing this, I was talking with some statisticians. They're like, you should write this up as a paper in a Stats Education journal. So I was like, okay. So I wrote it up with Daniela Huppenkopf and Aaron Springford and Tyler McCormick. And there's, on my GitHub, there's some example code and everything with the paper. So if you want to do this exercise, feel free to use this. Send me emails if you have questions, anything like that. Just watch out for the Canadian evidence. Okay, so back to the science. What I'm interested in for the Milky Way was the posterior distribution of the mass of the Milky Way, right? And so to do this, we can't write it all analytically like we can with this M&Ms example. So we sample the posterior distribution using some Markov chain Monte Carlo algorithm. And this is just a 1D example, but what an MCMC algorithm does is it walks through parameter space, gathers samples until it converges to a distribution of that parameter that is stationary. And so when you believe it's converged, then that stationary distribution should be proportional to the true posterior distribution. And then you can get estimates for your parameter and uncertainties and so on. Okay. So with the Milky Way, I use what's called a hierarchical Bayesian method. And this is to overcome these challenges that I mentioned before. So one was including measurement uncertainties in a model. So instead of treating the positions and velocities as known quantities, I'm now treating them as parameters in the model. We can also incorporate incomplete data by marginalizing over the components of the velocity that we don't know. So you can use both of these kinds of data simultaneously. We can also estimate that velocity anisotropy parameter, which is good. We have to make some assumptions about velocity anisotropy, but not completely. And then in the end, we get a posterior distribution for those model parameters, which we can use to estimate not just a single point mass estimate, but a cumulative mass profile for the Milky Way, which I hope can improve the interpretability. Okay, so I'm going through this again in pictures. So you can think of this hierarchical model as having a population level and then or having an individual level and then a population level. So at the individual level, every globular cluster has individual parameters, one for the true position and one for the true velocity vector. And then at the population level, the prior on that likelihood is that all of these globular clusters are following the gravitational potential of the Milky Way. And so as a population, they share the spatial density of the globular cluster population. They share the parameters for the gravitational potential and the velocity anisotropy. And then, of course, because we have parameters for our gravitational potential, we need to set hyperpriors on those parameters as well. And so this is where we can put in bounds for the model parameters. Maybe some of them have unphysical meanings, so we don't want to explore that part of parameter space. And so this is really how the hierarchical model is set up. Just to go through like the math a little bit, we're going to have the likelihood times the prior times the hyperprior. And we are assuming that at the individual level, the globular clusters are independent of one another, and that's why we can take the product of their probabilities. So we treat the true positions and velocities as unknowns. So in this case, this is just one example. The proper motion measurement is drawn from some normal distribution centered around the true proper motion and constrained by the measurement uncertainty. And then the prior on this, we use a distribution function of energies and angular momenta that's in the galactocentric reference frame. And so then we can pass this function h that transforms our parameters in the heliocentric reference frame to the galactocentric, and then use this inner distribution function to get a probability. And then we need, so the parameters for the physical model, there's 4 of them. We're using actually a really, really simple model. It's a power law for the gravitational potential, so there's a scale factor, phi naught, and there's a power law slope, gamma. And then for the satellite population, or these globular clusters, it's also following a power law, but with a different slope, alpha. And then there's the velocity anisotropy parameter for the globular cluster population, theta. So those are our 4 parameters in the model, and we need to set prior distributions for those model parameters. And so what we had chosen is a uniform prior for phi naught with some bounds, a normal distribution for gamma, a gamma distribution for alpha, and a uniform distribution for beta. Okay, so in the end, we're going to get this posterior distribution, do our Markov chain Monte Carlo algorithm, which uses some techniques that I brought in from the statistics literature. So we're using an adaptive tuning algorithm. And so what this does is it runs the chain for a short amount of time, and then looks at the covariance matrix of the chain, and then updates the proposal distribution based on the covariance matrix. And then you run the chain some more, and you iteratively do that, and it will actually help to tune the chain a lot faster. We also use what's called the R-hat statistic to monitor convergence. So we run multiple chains in parallel with one another, and then basically what R-hat does, it looks at compares the variance within each chain to the variance between the chains. And finally, we use a hybrid Gibbs sampler, and this is because we have a bunch of globular clusters. Every globular cluster has a bunch of parameters itself, so we're dealing with over 500 parameters. And so using a hybrid Gibbs sampler is a more efficient way of sampling that parameter space. And I can go into a little bit more about that afterwards if you have questions. Okay, so all the development and implementation of this hierarchical Bayesian method is in this series of papers. And in the end, you asked me what's the mass of the Milky Way. So this is our M200 measurement. It was 0.87 times 10 to the 12 solar masses. And this here is the 95% credible region for that mass estimate. And then we also get an estimate for R200 itself, and it's about 200 kiloparsecs. Because we have this posterior distribution, we can also get a cumulative mass profile. So using that posterior distribution, we can calculate the posterior at every radius, every distance from the center. And then we can look at this and say, okay, what's our mass estimate within 125 kiloparsecs? You can get a median or a mean and get credible regions with that right away. And it also enables us to compare how our model is doing compared to others in other studies. So I'm hoping that this provides kind of a more coherent picture of where we are in understanding the mass. Of course, this is assuming the model that we have assumed and the data that we have. Yeah.
Would you mind, where is exactly the data that you're using to start, like in terms of radius?
Yeah, no, that's a great question. So this was with globular clusters, and so a lot of them are within 50 kiloparsecs or so. Yeah, so that's why it's more constrained down here. There's a couple of globular clusters out here, but mostly not. Yeah, that's a good question.
So with that, when you have things like an anisotropy parameter, right, you can imagine there might be two families of globular clusters. Ones inside 50 kpc that are kind of virialized, and then a few globular clusters that are maybe falling in with some of the dwarfs and might represent a very different set of orbits, and statistically might be quite correlated, not independent at all.
Yeah, that's an excellent point. And so we did actually exclude some of the globular clusters for that reason, because some of them are associated with like the Sagittarius or the large nebula cloud. So we did exclude those, but we didn't consider, if some might have a different velocity anisotropy than the other ones. So that's a really good point. So this was actually a good segue into the next bit of research I did, because I got this answer and everything, and I was kind of like, okay, but I don't know the true mass of the Milky Way, so I would like to do some flying tests on simulated galaxies. And for my collaborators, Ben Keller, he does these hydrodynamical simulations of Milky Way type galaxies, and he had 18 galaxies. They were all very different, they're complicated, definitely more complicated than the model that I'm assuming. And so we thought it would be fun if he just gave me the kinematic information of globular cluster type objects in these and didn't tell me what the mass was of the galaxy.
Are they cosmological? Like, are they cosmological zoom-ins?
Yeah. Yeah, it's like some much too. Okay. So they can't create globular clusters in these kind of simulations yet, even with the resolution and so on. So what Ben did was he went through and grabbed these globular cluster analogs. So each particle has a mass of about 10 to the 5 solar masses, which incidentally is actually pretty close to globular clusters. They picked ones that were low in metallicity and that were really old. So our hope was that they were kind of representative of globular clusters. And then he gave me the simulated data, which were the galactocentric positions and velocities. And he also removed ones that were in the disk for the various reasons that David was just mentioning. And then I took these and I transformed them into heliocentric values and also created mock observations. So I removed 50% of the proper motions, also introduced an observational error in both distance and velocity, and then we subsampled them so that we have a number of clusters that were similar to our actual data set. So I did this, and the very first galaxy I looked at, I got this prediction, and I sent it to Ben and said, here's our virial mass estimate. And then this is verbatim what he wrote back. He was like, looked like the method worked pretty well, shockingly well, actually. Here are the numbers direct from these simulations, and they matched really well. And I was super surprised because the model we're using is so simple, and these galaxies are actually really complicated. So I was surprised by this. But if we look a little bit closer and look at the cumulative mass profile, then we can see that it actually doesn't fit the data that well. So yeah.
Did you test how important those assumptions you made earlier were? Like you picked a certain subset of the dark matter particles, right, to act as your globular clusters. If you just picked something else, would you have done lots worse than this, or did...
That's a good question. We actually, we didn't look at other particles, and yeah, that's something that we could do. Yeah, that's a good idea. What about that? Yeah, so here we can see, even though the virial mass was estimated quite well, right? You can see that in the inner regions, the model is having trouble explaining the data. So the red line is the true cumulative mass profile, the gray are basing regions. And so what I think is happening here is that maybe the gravitational potential doesn't actually follow a single power law, and so it's making some compromise between the information it has in the outer regions and the inner regions. So we repeated this for all 18 galaxies, simulated galaxies. And the true estimates are the blue diamonds here, and the true values are the blue diamonds, and our estimates are the purple dots with the 95% credible regions. And you can see for the most part, the true values do lie within the 95% credible regions, although they seem to be somewhat underestimated. There's a couple exceptions, this one and the one over here, I think. This is the worst one. But this one, it turns out, had a companion next to it that was very, very close, and so we were sampling tracer particles from that companion that was like infalling, so that kind of explained it. Okay. So we did this one test, and kind of, it gave me a little bit more confidence in what we're doing, but also gave me maybe a hint that there could be some bias in our mass estimates, that it could be a lower could be giving a lower mass estimate. But it's all conditional on the data that we chose and the particles that we picked. But we did this because we knew Gaia was coming, and I wanted to know how Gaia would do once we did have proper motion measurements for a bunch of globular clusters. So April 25th, 2018, the Gaia DR2 release happened, and so we reran our model with the complete velocity information for the globular clusters and got a new mass estimate. And actually, it's lower than our previous one. And I think part of the reason might be because of this bias that we could have in our model. But what is interesting, actually, is that when this Gaia data came out, there were a bunch of papers about the mass estimates. So there's even more now as well. But a lot of people reported the mass within about 30 or 40 kiloparsecs, and they're all around here, and we all agree with one another, even though we're using different methods and different approaches. So I think that's really encouraging, that having complete data might help us constrain the mass better. And it kind of makes the case to get more data at further distances as well, where it's still in large distribution. Okay, so I talked only about globular clusters, so that would be the blue, so the blue orbits drawn on this diagram. But there's also, of course, dwarf galaxies. And so this is what I've been doing currently at UW. I have some undergraduates I'm working with. So while I was at UW, Annika is an undergraduate, so she was looking at the dwarf galaxy proper motions from the Gaia data and using my method to estimate a mass using those. We're also collaborating with Mario Urich, Robin Sanderson, and Andrew Wetzel. We're working with them because we're using the FIRE simulations to help set our prior distributions on the spatial distribution of the dwarf galaxies. Okay, so this is super, super preliminary. So. But it does look like when we look at the dwarf galaxies, we're getting a much higher mass estimate. So I think that's really interesting. So that was using only the roughly 12 dwarf galaxies measured by the Gaia collaboration, but there's a bunch more. So here's an example from Fritz, 2018. They have velocity measurements for 39 dwarf galaxies. So now we're looking at these, and these ones have a bigger range of bigger spatial range. So this is just to show kind of their spatial distribution. I have the proper motions on the vertical axis, distance from the center of the galaxy along the horizontal. The blue dots are all globular clusters, and then the diamonds of the dwarf galaxies. So they are really probing much further into the dark matter halo. And one question might be, well, which dwarf galaxies are in equilibrium with the Milky Way and which are not? And is the velocity anisotropy actually constant for these dwarf galaxies? So what Riley et al. Have done is they've already started this research and made a cut of 100 kiloparsecs and looked at the velocity anisotropy for dwarf galaxies beyond 100 and then within 100. Oh yeah, and I just did that so you can see the dwarf galaxies. And so this is what Riley et al. Have found, and so the green line on the right here, that's their posterior distribution for beta if you only look at the dwarf galaxies beyond 100 kiloparsecs. And it's quite different than if you look at the ones within 100 kiloparsecs. And so what I think is interesting here is how would this affect our mass estimate? Yes?
So some of those dwarf galaxies were quite far away, right?
Mm-hmm.
So at some point, I guess it will be best to jointly model it together with the Andromeda galaxy's parameters.
For Andromeda, is it?
Yeah, because you can't
like
look at the Milky Way. Yeah, exactly. Yeah, so it's still much closer to the Milky Way, but I was thinking that eventually you'll have to think of it as the sum of the two potentials rather than just.
Yeah.
I think the LMC will matter first.
Yeah,
It's
the LMC
bigger.
too. Yeah, sorry.
Yeah. So one thing that we're doing is asking how might these different velocity anisotropies actually affect our mass estimate. So I have a couple undergraduates at the University of Toronto that are doing sensitivity analysis. So one is using this cut that Riley et al. Has used and is getting a mass estimate for those dwarf galaxies within 100 and outside of 100. And that Xander and then Kesslin is going to be doing like a jackknife analysis to see which dwarf galaxy might have the most equilibrium mass estimate. Okay. And there's lots of other areas to pursue with this kind of hierarchical Bayesian model. In terms of the Milky Way, I think ultimately we want to be able to combine all different types of data at the same time. So that's the kind of long-term goal I have. So they, within some distance from the center of the galaxy, maybe you can assume that everything is following the potential of the Milky Way, but they have different spatial distributions. So you need to model those different populations separately. Also, I'm interested in doing Bayesian model comparison tests and model averaging, because in the literature, people are using different models, and I don't think there's been a really thorough investigation of how these different models perform. And then there's also transferable applications. So you're using this method to estimate mass distributions of globular clusters or in elliptical galaxies or in dwarf galaxies. And I've just started working on some simulated globular cluster data to see how this work. Okay, how much time do I have?
About 25.
Perfect. Okay, I'm running out of left. Okay, so now we're going to change gears and talk about stellar time series. And what I hope is an improved method for time domain astronomy. And this is going to be in the context of astroseismology. And we know that time domain astronomy deals with time series analysis. In statistics, sometimes they call this spectral analysis, which can be confusing, but that's because they're talking about the Fourier domain, so they're talking about the spectral analysis part of it. So if I say that, I'm sorry, I don't mean like spectra. Okay, so just to start from basics again, we know that our sun is a medium to low mass star, and we know it has these different regions, right? And we assume it's in hydrostatic equilibrium, so there's some radiative and thermal pressure outwards, and then you also have a gravitational force inwards. And then there's all these different zones, right? You have the convection zone, the radiative zone, and the core. And these different zones create boundary conditions. And so through the convection that's going on in the convection zone and these different boundary layers, you can actually set up standing waves inside of the star. And so this is how you can get things like P modes and G modes. So I'm really just going to talk about G modes in this talk, or pressure mode oscillations. You can also think of them as sound waves inside of the star. And what's great about these pressure waves is that they can actually, if we can measure them, then they can tell us about the interior of the star. So people have done this for the sun. They look at the sun over time, collect some time series data, and then look for signals in the frequency domain, right, that have some periodic signals by looking at the power spectrum. And the power spectrum, or power spectral density, is really just telling you like how is power distributed across the different frequencies. And so if you have some strong periodic signal, then you should see a peak at a certain frequency in the power spectrum. So the power spectrum for the sun has been well studied. Here it is. And what's interesting is the spacing between the modes and the height of the peak mode. Because the spacing between adjacent modes can actually tell you about the mean density of the star. And the peak mode is related to the mass, radius, and effective temperature of the star. And so if you have a separate measurement for the effective temperature of the star, then you have two equations with two unknowns, because you can write the mean densities and a bunch of mass and radius. And so you can solve for the mass and radius of the star if you measured nu max and delta mu. And so astroseismology is doing the same thing, but for other stars, right? And this is really handy because we want to measure these stellar properties that are interior to the star and test our theories about stellar evolution. And stars that astroseismologists commonly look at are red giant stars. And that's because they have this very large convective zone that are thought to excite P modes, or solar-like oscillations. And these could help us answer questions like, how common are these solar oscillations of red giants? Can we identify different evolutionary stages of red giants? What are the range of masses, radii, age? Is there internal rotation? What's the depth of the convection zone? All of these things could be answered through astroseismology. So we can look at stars over time, collect some time series data, look at the subtle changes in the light, and get an estimate of our power spectrum and measure these astroseismically. But it's a lot more difficult with stars that are really, really far away. Right? So there's all sorts of measurement errors, and we can't always resolve the star, and so on. So here's an example of a power spectrum of a red giant star, and you can see there is a hint of these solar-like oscillations. But there's also a lot of other noise going on, and people try to model things like the background model, any noise that's in your time series, if there's granulation on the surface of the star, all these things you need to take into account. So these challenges in astroseismology is that we can't always resolve the star's surface. Another challenge is that the classical periodogram is a poor estimator of the power spectrum. I'm going to talk about that a little bit more in a second. And then, of course, our data in astronomy is often unevenly sampled in time. So we can't grab all of those time series analysis methods from stats because a lot of them are for evenly sampled. Okay. So why is the classical periodogram a poor estimator of the power spectrum? And I'm going to show this through an example that I didn't come up with. It's in a book by Percival and Walden. But what it does, it uses an autoregressive process. So imagine we have some data xt, okay, and at every point xt depends on the points before it, xt minus I. And this autoregressive process could be of order 1 or 2 or so on. So you would say an autoregressive process of order 3, then every xt would depend on the 3 t's before it. Okay, so if I generate some, just a toy signal from an autoregressive process of order 4. So here's my time series data. There's 1,000 points. And this is evenly sampled data. The true power spectrum of an AMOR4 process is known analytically, so you can actually solve for that. And it looks like this Batman shape. So you're like, okay, that's the true one. And then if we take the power spectrum of our actual data and look at the estimate of the power spectrum, then it looks like this, and you can kind of see the Batman shape, so you're like, oh, okay, that's good. But when you actually compare it to the truth, you can see that there's some bias. And so this is one problem with the periodogram, is it's a biased estimator of the true spectrum when n is small. And the size of n that would make it unbiased is unclear. It can depend on the process that you're looking at. It is asymptotically unbiased, so as you collect more data, so here's one where it generated a time series of 10,000 points, you can see the bias starts to go away. So it is asymptotically unbiased, but it's also inconsistent. And so what that means is that the variance of this estimator does not go to 0 as n goes to infinity. So here's, to show that, here's the periodogram estimate, power spectrum estimate for 50,000 points, and you can see that there's a lot of noise and it's a high variance. Okay, so these are the two main statistical issues with the periodogram. And these come from something called spectral leakage. These figures are from Jake Vanderplas's paper about the Bolon-Scargo periodogram. So in this example, we have some time series that is occurring in nature, okay, and it could go infinitely off in both directions. Okay, if we take the Fourier transform, then this is what that signal would look like in the frequency domain. You see these perfect spikes. But we don't observe objects in space for an infinite amount of time, right? Our telescope is off, and then it's on again, and then we turn it off again. So we have some window function that we're actually looking at the data. So in the time domain, we're getting a pointwise product of this time series, right? But the thing is in the frequency domain, this sort of box or hat function in the frequency domain is a sync function. And so you can see it has all these wiggles as you go out from the central frequency. And so a pointwise product in the time domain is a convolution in the frequency domain. And so you're going to get this spectral leakage that leaks power into adjacent frequencies and makes your power spectrum estimate more easy. Okay, so what people have done to try to overcome this is they'll taper the data. And tapering the data means you're going to multiply your data by some function that's going to downweight the discontinuities at the end of your window function. And so there's many different tapers. There's a good paper from back in 1978 by Harris, and they look at all the different tapers that people have kind of looked up to that point and compare their performance. I'm going to show you just a series of examples, but you'll see the window function on the left, and then its Fourier transform on the right. So there's a triangular window. This is a Hamming window. There's also one called a Han window, and those are different, and sometimes people call the Han the Hanning because they're so similar, but they're not the same thing. Watch out for that. This is a Tukey window. So you can see these all might have advantages in certain applications over others. But there was a big breakthrough in 1982 by David Thompson. He introduced the multi-taper estimator. He did this while he was at Bell Labs, and the story goes was that his supervisor came to him and said, "Find me the best taper." And it turned out that the best taper was multiple tapers. And so this is why it's called the multi-taper. So the multiple tapers that you use come from this special set of functions called the discrete prolate spheroidal sequences, or DPSS. They were discovered by Slepians, so they're also called the Slepians. And what's special about these is they come in a bunch of different orders. So the blue line is the first order, the green line is the second order, and so on. And each order is orthogonal with all of the other orders. So what you can do is you can take your time series data and you taper it with the first order, and then you get an estimate of your spectrum. And then you take your time series again, and you taper it with the second order and get a second estimate of your spectrum, and so on. And because all of those tapers are orthogonal with one another, that means that all of your estimates of the spectrum are independent. And then you can multiply them together and get a better estimate of your power spectrum. And so by doing this, this reduces the spectral leakage between adjacent frequencies, and it also reduces the bias and the variance. And so this became a super popular approach in signal processing and all sorts of areas, but mostly in engineering, where they have controlled experiments and they have evenly sampled time series. So I think this is why it hasn't really shown up in astronomy yet. So if we go back to our AR4 example, right, this was the estimate of the power spectrum from the regular standard periodogram. And then the black line here is the multi-taper estimate. So you can see it does a lot better at estimating the true power spectrum. Like I said, this is for regularly sampled times. And we have unevenly sampled data. So what do we do? Okay, so here's an example of unevenly sampled data. We have this red giant star, Kepler 91, and there's gaps. The data is unevenly sampled, so it would be nice if we were able to use the multi-taper with this type of data to look for astroseismic fields. But what we usually do in astronomy is we'll use the Lomskargel spectral estimator, because this does deal with unevenly sampled times. The Lomskargel is the periodogram for unevenly sampled times. And it has some good properties, so it's invariant under time translation. It is also equivalent to just doing a least squares fit of a sinusoid to the data. So if you're looking for just one signal, it's great. Like, you should definitely use the Lomskargel. But it has some not so good properties too. And one is that its spectral leakage is actually worse than the periodogram. And identifying anything other than one dominant frequency can be really difficult because of this spectral leakage. So I'm going to go back to Jake Vanderplas's plots here that he has. So again, imagine we have, it isn't even a periodic signal, but just like a maybe a transient object or something. If we were to look in the frequency domain, it would look like this. But if we observe this object at a very unevenly sampled times, then when we do the pointwise product, this would be essentially what we have. Our window function, or sorry, our data would look like this. And so when we go to the frequency domain and we're now convolving, right, the Fourier transform of this window function with that signal, all of a sudden we get a really messy looking periodogram. And you can see there's all sorts of peaks that you might mistake for being a true signal. And I believe that Skargel actually warns about this in his paper. He says this is really useful if you have a single frequency, but if you're looking for multiple, it might not be the best approach. So is there a multi-taper for unevenly sampled times? And because if there was, then maybe it would be useful for looking at things like astroseismic fields. There is a generalized solution, released from Ronez 1988, but it's really difficult and expensive to compute, and that depends on the length of your data and all sorts of things. So it really never got any traction. I mean, maybe nowadays, maybe it would. I haven't looked into it. But one of Dave Thompson's students, Aaron Springford, for his PhD thesis, he came up with another approach to this. So what he did was, instead of calculating these Slepians on their own, because that's really what's expensive, he approximated the Slepian weights with splines, and then combined that with the Lomskargel to create the multi-taper Lomskargel approach. And so the result isn't optimal for some arbitrary, unevenly sampled times. So you always want to look at sort of the window function of how you've sampled your times. But it is identical to the multi-taper estimator if you have regular sampling. So that's a nice feature. and it's really fast to compute. So if I have this time series data, this was given to us by Tim Betting, and it's been pre-processed and everything, because I'm not an expert in Kepler data, so I didn't know how to do that part, but Tim kindly gave us this, and so I went to her and I said, I think that your method could be really useful for this, so let's try it with the multi-taper Lomsgargle. So here I'm comparing, this is the Lomsgargle periodogram estimate, power spectrum estimate. You can see there's the hint of these astroseismic modes. And if we apply the multi-taper Lomsgargle, it looks like this. And you can see the astroseismic modes a lot clearer. So when I saw this, I was very excited because it seems like this could be a really useful method. And we've submitted a paper to AJ, got the referee report, it's quite positive, so we're just, filling in some things that the referee wanted to add us, and I'm really hoping we get it resubmitted like by the end of the month. And then we'll have some code to release it as well. Yeah, my hope is that this is going to obviously help us estimate these parameters that we want to know, right? Like the spacing between the modes and the max mode. Okay. And in astronomy, it's not just astroseismology, right? There's all sorts of time series data coming. And there's lots of periodic phenomena in astronomy, like stellar rotation, binary systems, variable stars, black hole accretion, stellar spots, all sorts of things where maybe this would be useful. I don't know, I'm not experts in these areas, but if you are, please talk to me. There's also lots of archival and new time series data to explore with this method. And of course, we have the Zwicky Transit facility and the Vera Rubin Observatory now as well. So I'm very excited for trying to make astronomy into the 2020s. And having methods that are fast to compute are going to be important in this era of large surveys. There's also the Canadian Hydrogen Intensity Mapping Experiment, so this is in BC. And they look at things like gamma ray bursts and stuff, so they also have time series data. Okay, so I'm hoping that the takeaway from my talk is that model uncertainty and the methodological approaches are becoming the limiting factor in astronomy. And I believe all of you know that already because you're all here at the Center of Computational Astronomy. And I think that this interdisciplinary collaboration really has a lot of potential because these things wouldn't have been possible without collaborating with statisticians. And so it has the potential to improve statistical inference in astronomy and make new discoveries, but it also can inspire new statistical methods as solutions to complicated problems. So I think on both sides it can be interdisciplinary research can be useful. Of course, translating between disciplines can be really difficult, but I do believe that the rewards are high, and it's worth investing in that. So I am building an astrostatistics research team. So if you know any good students that are interested in graduate school or postdocs, please send them my way. And they'll have an opportunity to collaborate with statisticians, computer scientists, data scientists, and astronomers at U of T. We have some great institutes like Dunlap, there's the Fields Institute, Vector Institute, and there's the Canadian Statistical Sciences Institute of Ontario as well. I'll stop here.
Yeah, I was just curious, when you use the Gaia proper motions, did you still exclude globulars based on them being associated with maybe Sagittarius and LC? And if yes, how did you do that exactly? Like, do you do metallicity, orbit?
So we use ones that have been identified in the literature by other studies, and I think those people have looked at metallicity and maybe their kinematic properties. But I didn't actually look too deeply. I just trusted that what they had done was good and kind of said, okay, I should take those ones out. But yeah.
This is with these sweeping wave functions. They are solutions to quantum mechanical equations. Yeah, they're solutions. You have square bell potential. They represent the different energy level solutions.
The Slepians.
Slepians.
Oh.
They're compact. Yeah.
They
Slepian's
learned.
original paper is brilliant.
Okay.
And you can use that to generalize the Slepian functions, right? So that's, the Slepians will write things when you have square but hit walls, right? But if you have a different shape potential, because you have different spacings, you could actually solve the Slepians. You'll solve for the equivalent functions in that space.
Huh.
And I'm wondering if people have thought about this in this context.
Yeah,
right?
because
So-
you essentially have walls
Yeah,
in a way, yeah.
so this is used by the geoscientists doing seismology. Not stellar seismology, but seismology on Earth.
Yes.
Right, and you've got your samples distributed around, say, Africa, and you've got this uneven boundary condition, uneven sample. And they-
Spatial case.
In the spatial case. So they do that, and I wondered if this could be transferred.
It could be. So actually, I should mention there's a paper very recently put out by Alan Chave, and he has developed another method for unevenly sampled data using multi-taper. And I think he works on on seismology data. So I wonder if that's application that he's looking at.
It could be. There's some
Yeah.
papers by Frederick Simons,
Okay.
who applies this unevenly sampled papers in geosciences,
Oh, okay.
and does multi-taper for unevenly sampled data. So it's the same spirit,
Yeah.
and I wonder if some of that might be transferable.
Yeah. Yeah. I should. Thank you. I've been also thinking about like interference data as
Mhm.
well.
Maybe left
Oh,
next.
sorry.
to
This is
her.
all the-
I just was gonna ask, I don't know if you saw Dennis Urkel's paper
That was
today.
my question.
Okay.
No.
Yeah, probably.
She was
Well,
telling me a little bit, but.
Yeah, just that including the LMC and mass estimates, if you don't include the LMC, then you're biased high in your mass estimate of the Milky Way. And I was especially interested in your comments on that, given the preliminary work that you showed, showing that the mass of the Milky Way was
Yeah,
biased.
yeah, so that mass estimate wasn't using the LMC.
Right.
We left that one out. But that's one reason why we're doing the sensitivity analysis. Those are the other two undergraduates I'm working with. Because I think it's been suggested that there's kind of a radius from the center of the Milky Way at which the LMC hasn't really had an effect yet. And then beyond that, it might have had an effect on the other dwarf galaxies. And so our model is essentially assuming equilibrium. So are we going to get a different mass estimate using the dwarf galaxies within the radius versus outside if some of them are not in equilibrium? Yeah, we're exploring that.
Right.
Yeah. Great question.
And I had the same question, but also just adding to that, that you could probably do all different scenarios, right, and see how your results. And I think it sounds like they very exactly like Dennis Peterson, they would.
Yeah. The what variable?
The mass estimates,
yeah,
if you
yeah.
include or exclude them.
Any questions for Gwen? I actually had one. So you mentioned model uncertainties being a major issue, and I was specifically about the Milky Way potential. If you thought about exploring different models and doing model comparison.
Yeah, that's definitely something I want to do. I just haven't had the time yet. So I think one thing that you could do is like the Bayesian model averaging. I think is really interesting. So you get different posterior distributions given different models that you assume, and then you like evaluate the fit of those models and then weight them accordingly, and then you can get sort of an average. And I think that might be nice because then you could get a cumulative mass profile for the Milky Way that kind of encompasses what all of the literature is saying about the Milky Way. And I'm guessing the error bars would be very big, but at least then it would kind of be like a holistic view of where we are.
Well, let's thank Gwen again.